Alright, we'll start the screencast talking about alloys. We're going to describe alloys as a homogeneous mixture of metals, or a mixture of a metal and a nonmetal, and then explain how alloying can modify the properties of metals. So, why is steel more useful than pure iron? We should be able to answer this question at the end of this screencast. So let's define an alloy first. An alloy is a homogeneous mixture, meaning you can't see more than one phase, it's well mixed. So it's a homogeneous mixture containing at least one metal combined with another metal or nonmetal. Normally when you think of homogeneous mixtures, you tend to think of a liquid phase. Alloys are made in the liquid phase, but then they can be a metal, solid, at room temperature. And because of the different compounds that may be added to metals or mixed together, alloys often have superior properties to those of the pure metal. And of course that depends on what properties you're looking to impart. So looking at an atomic view of a pure metal versus an alloy, hopefully you can see this would be the pure metal with all of the atoms being the same, and this would be the alloy with additional compounds added or metals added. In the metal, these atoms easily slip by each other, making it malleable, ductile, sometimes referred to as softer. Here, because it kind of, these additions disrupt that pattern, they're typically stronger. Right, if we add carbon to the iron, there's a low carbon type steel, percentages 0.07 to 0.25%. These are easily cold worked and used typically for car bodies. Higher carbon is wear resistant, not as easy to work with, and those are cutting tools, so they're definitely harder and used in applications where that property would make sense. Here's a table of the different alloying elements and the properties given to the steel when these are added, and then the uses for the different types of alloys. Heat treatment of steel. Heat treating of metals is really important in industry. And to treat the steel correctly for the application that you're going to use it in. The purpose of heat treating is to change the properties of the steel. And there are three basic types of heat treating: annealing, quenching, and tempering. And sometimes they use all of these depending on what it is they're doing with the steel. Annealing. Annealing is when metal is heated to a temperature 1,000 degrees Celsius. It actually depends on the metal. But the process is you heat it and then you cool it slowly. And what this does is it allows the structure to recrystallize by forming new grains and growing larger grains. The textbook, Catherine Brown, says that the metal recrystallizes into smaller grains. I'm not exactly sure that's quite true, but this whole heat treatment of metals is a study unto itself. Material science delves into this and materials engineering into a much greater degree. But the overall effect of annealing is that it does give you a more malleable and a ductile metal, and it is frequently done after the metal is cold worked. I want to skip a couple slides and show you just some pictures of what this really looks like. This is the picture, a sample of metal, and showing you the grained boundaries between those crystalline structures. Blowing a small section up, these lines here are what are known as the grain boundaries. And if you notice, the atoms in a single grain are fairly regularly arranged. The more grain boundaries you have, the more brittle the material is. Now this one shows the formation. I think you've cold worked the material, and when you add heat, it forms these new grain boundaries. And I think over time they grow into larger grain boundaries, and that replaces some of the malleability of the metal, because the larger the grain size, the more regular these atoms are, metallic atoms, and the easier they are to slide over each other, as opposed to at that grain boundary. Then we have quenching, and this is heating to a high temperature and then cooling quickly, and that's done by either immersing into cold water or sometimes oil. And this reduces the crystallinity. It traps alloying metals into the crystal grains. Cooling it slowly allows those alloy materials to kind of come out of the metal. The effect of quenching is a much harder metal. It is more brittle. Tempering is sometimes performed after quenching, and that is heating the metal to a lower temperature, 200 to 300 degrees C, for a period of time, and then slowly cooling it. And what that does is reduce the internal stresses in the metal that are sometimes imparted through quenching, but still keeps the added metals making the alloy within the metal structure. Okay? And the effect is that it is more malleable, more ductile, less brittle. And again, you're working with that crystalline or that grain structure.